Hello and welcome to our Fundamentals of Systems talk. It's good to start at the beginning whenever you're taking on a big endeavor, like understanding an entire computer and how to write code that functions as best as it can because you have a full understanding of the computer that your code is running on. So we're going to take a big step back, not just to computer systems, although that is the focus ultimately of what we're discussing here, but knowledge that can actually help us understand any system. What are its boundaries? What are its interfaces, its components, its linkages? How do we decompose a system? And finally, we'll take that knowledge and then see how we can apply it to understanding at a very high level how computer systems actually work. How do their processors work? And how do their processors talk with memory? Let's start with the definition of a system. So a system is a collection of components. These are the parts that make the system up. In the computer, you can think of the monitor and the CPU and the keyboard and the mouse all as components. With the memory is, the hard drive, all of these things. In a car, you can think of the wheels, the brakes, the fuel system, the engine, the transmission. So these components are, individually actually their own systems, and we're going to talk about that in a moment. But to make a complete system, they have to be linked together and organized in such a way that we recognize it as a single unit. All of those parts of a car, like a transmission, we recognize maybe what a transmission looks like if we see it laying on the ground, but for it to be a working part of a car, we know that it has to be linked to the engine and linked to the wheels, and it has to be able to perform its function. It needs some kind of linkages, and there needs to be organization on how all that comes together. This is no different for a computer. We need to plug our monitor into our computer. We need to plug our keyboard inside the computer. We need to have graphics cards or chips and memory plugged in, right? All of these things need to come together. That's what we're looking at here, right? We're looking at how do these things relate. Linkages, by the way, can also be called relationships between these components. Let's look at another system to kind of better understand these linkages and how they work for us. A plumbing system has fairly well-defined components. It's also very easy to kind of separate your plumbing system from the rest of its environment. It's pretty easy to kind of differentiate that. I know, for example, that my door is not part of my plumbing system, and my printer is not part of my plumbing system, but my sink is, and my tub, and my toilet, my water heater. And what are the things that link all this together? And for a plumbing system, that's relatively easy to answer as well. It's usually pipes. Now, there might be different types of pipes. There's pipes that are high pressure. There's pipes that don't have any kind of pressure rating at all. There's pipes that deal with waste, and there's pipes for heat that can deal with higher temperature water. All of these things, they have variation. There's different diameters to pipes, different materials. There's different ways to link pipes together. So you can sweat pipe, which is, with a torch and some solder, or there's newer ones now where you can crimp and use pressure to bring the pipes together. So the linkage between plumbing system is very straightforward and very easy to understand. But not all systems have, such discrete number of linking. So if you think of a car, for example, components might be linked by wires because electronically these things are linked together. Might be linked by hydraulics. Say your braking system, you press on the pedal, you have a master cylinder that pushes fluid through lines, and those lines send the fluid to the brakes, and the pressure actually pushes a little piston inside the caliper, and it squeezes the brake pads closed on the wheels, right? Another way that you could have a linkage is any kind of mechanical linkage. Older steering linkages, for example, were mechanical. Between the steering wheel and the wheels was a series of universal joints and metal rods. You turn the wheel, you are physically turning the wheels on the ground as well. In fact, while we're talking about automotive systems, let's just take a moment to say, how much variety there can be in any one given system. So we look at a car and we say, okay, a car is a system, but there are so many variations of cars. There's gasoline cars, there's electric cars, there's hybrid cars, there's self-driving cars. Self-driving car has many more computer-related systems than any other modern car, and modern cars have a lot of computer systems in general. So understanding a system is important, but understanding those individual components of the system is why we want to do that. And we also need to understand the environment that the system works in. What are the parts that are important to know for my system? For example, a car drives on a road, right? The road is part of the environment. It's not part of the car, nor am I, the driver, part of the car, right? I'm part of the environment as well. I am an important part of the environment, and so is the road. Now, why is that? And the reason is because we need interfaces with our system to talk through these important parts. So the car needs an interface for the road, and that's our tires. And there's a lot of thought that goes into tires. What rubber compound are they? How long will they last? How sticky are they? How do they do in different temperatures, in cold and heat, right? All of these things are things we need to think about the interface between the car and the road. The interface between me, the human, and the car is things like the steering wheel, the gear shift, hopefully it's a manual one, the gas and the brake, right? The parking brake, the gauges, right? They tell me what the car is doing. So these are our interfaces. And in computer science, this is a very, very important concept because even in software, you've probably heard the term application programming interface. What we're referring to here is the gateway into the system, the software system in this case, that we are building. And a well-defined software interface means that anyone can use your software system simply by understanding the interface. You can drive a car simply because you know how to use the interface. You know how to use the gas pedal, the brake, and the steering wheel, and all of these things, right? And this is true of computers as well, both hardware and software. If you're designing a computer chip and that computer chip has a universal interface in which to insert it onto the motherboard, all you need to do to build a new chip is to understand that interface, assuming that you're reusing the same one to connect to existing motherboards, right? And then you can build a new chip on top that links to that interface. I want to take a moment now and talk about a slightly different type of system, and that's the solar system. Now, the solar system has pretty well-defined components. We have a sun, obviously our star. We have the planets, including Pluto, although I know it's a dwarf planet, so we have dwarf planets as well. We have the asteroid belts, and we have, comets possibly. And that leads us to the next question, which is, well, how do we define what's inside our solar system and what is in the environment? How do we know where this boundary is? What are the linkages that hold it all together? Well, unlike the systems that we've discussed so far, the solar system doesn't have a physical linkage. It has a conceptual one, and of course that's gravity. Now, you might think, wait, isn't gravity a physical force? Well, without going down that rabbit hole, although it would be a very fun one to go down, I don't pretend to be a physicist, but from what I understand, Albert Einstein said in his theory of general relativity that because mass gathers in particular places, that distorts space-time. And that distortion of space-time is what we're actually feeling as gravity. So I'll leave that for somebody who knows it better than I do. But the point here is that this is a phenomenon that is not a physical one. It is a conceptual one. And what's important is that systems are okay with that. Linkages and components can be conceptual in nature. There's no requirement that they are physical at all. Let's look at another example of this idea. So a computer network is a great place to start because we have both physical and conceptual linkages. You can have Ethernet connections, which are physical, and you can have wireless connections, which send radio wave through the air in order to send information back and forth, right? So this is one more example. But we can also look at something like a software system that is actually completely conceptual. There is no physical components to the software system. Now, the software system might exist and run on physical components, such as storage on a magnetic medium or running through a processor. But the software itself is completely conceptual in nature. Now, a software system like what we see on the right-hand side here, which is what's referred to as a ERP or Enterprise Resource Planning software, can be very complex, and it can consist of many modules. There might be a module for general management of users. There might be this particular one is for a school. There might be a module for students. There might be a module for finances. There might be a module for HR, right? There might be all these different pieces that are, in a way, their own kind of separate subsystems. The linkages between these are the APIs that they use to talk to each other, and it's all virtual. The code is virtual, the linkages are virtual, the components are virtual, all of it is a virtual system. Systems do not need to be physical at all. Now that we understand what a system is, how to define it from its environment, how to talk to it through an interface, let's look at what kind of superpowers that actually gives us. That gives us the ability to do what's called decompose the system. Now, if you look at this phone here, this phone is a system, right? This phone has many different components, a screen, it has a processor, it has memory, it has a camera, it has accelerometers, gyroscopes, all kinds of sensors. All of these things come together to make this work. And of course, there's linkages, mostly buses, which we're going to talk about, that link things together between different circuitry. But if I want to build this phone, that's a relatively difficult task for any one person to undertake. What I really want to be able to do is decompose this phone and then take different components, say like the camera system, the battery system, the screen system, the motherboard with the CPU and memory, and break them apart so that people can specialize in them and be able to work on those particular systems. So we can have engineers that are responsible for making the best camera system and engineers that are responsible for making the battery last longer. And all they need to know is what are the linkages, what are the interfaces that link their system with the other subsystems that make up this whole phone, right? So this is the idea behind decomposition. Any system is generally going to be composed of other subsystems. A component may be a subsystem, or it may actually be irreducible. You can get to the point where you say this is no longer reducible. Perhaps you decide that's at the transistor level, right? Like a transistor is something I can no longer break apart. I guess that would be a debate with the physicists, but that is the basic idea here. We want to understand our system so that we can decompose it. Now, an important thing to note is that this only works from the top down, right? We can understand a phone's components and understand the phone as a whole only when we view it from the top. If I start with just a accelerometer sensor from this phone, I can't understand the whole phone, right? Because I don't know what other systems are involved. I have to start from the top down, right? I have to kind of decompose starting with a holistic view. Same thing with a car. I can't understand an entire vehicle just because I have a brake caliper. I have to start from the car and work my way down to that brake caliper. So understanding systems and the properties, the relationships, the connections, the constraints, all of these things that we've been talking about allow us to understand collectively what we know as the architecture of the system. So when you hear me use the term architecture, this is this concept that we're saying for some actual object to fit the definition of, say, a car, it needs to abide by this architecture. It needs to have these components with these interfaces. I haven't necessarily said, say, what the output of the engine has to be, right? I haven't necessarily said that it has to be a 500 horsepower engine versus a 200 horsepower engine. I've just defined that the car has to have an engine. I haven't even necessarily said that the car has to have a gasoline engine, although that might be defined for a specific architecture. You might have a gasoline car architecture versus an electric car architecture. But what's important to understand here is that when you're talking about the architecture of a system, you're talking about the high-level concepts that need to come together to make something work. Now, we're going to later look at the word architecture with a capital A when we're talking about specific computer architectures like x86, ARM, PowerPC, MIPS. These are particular architectures, just like a gasoline car is a particular architecture. So now that we understand a system, let's talk about a very high-level way we can use these concepts to define any computing device. Any computer, whether it's a desktop, a phone, a tablet, an Internet of Things device, anything that does computation for us. The most basic way to describe it is something known as the input process output model. It's also known as the input process output storage model because storage is something that, in fact, it does need to do. We can visualize it this way, where some input is provided, whether it's by a person or another system. We're going to perform some process on that. Let's say that we're adding two numbers. The input are the two numbers that we want to add. The process is the act of adding them. The storage is our memory. Now, this doesn't have to be thought as permanent memory. It does need to be there in order to work with the data that you are manipulating. It might not be remembered, it may, but you need storage in order to just have memory, to have machine instructions and data. Now, the output of this is our output. Any computing device fits this model. A stored program computer is a computer concept that we can use to define a little bit more specifically a modern computer beyond the input process output model. So we're going to start with that. Stored program computer is an input process output model computer, but it more specifically says that computer instructions, what we would think of as our code, and data both live in memory. So, and they can coexist in memory in any location. This might seem very intuitive, but there actually was something that came before it. This was developed by von Neumann and other researchers that were working in Princeton on an early computer you may have heard of called the ENIAC. And while they were working on this, they realized that it would be advantageous to, instead of having a plug board or some other kind of read-only memory where a program was written and basically written once and could only ever rerun unless you had a plug board and you rewired it. It would be great if we could use a rewrite memory to store different programs. That way the computer could run any program that's in memory, not just what we hardwire. This was a big evolution in the way that computers could be used in a general purpose sense. Now, von Neumann went on to define what we know as the von Neumann architecture, which is also an evolution of the input process output model. It uses the stored program concept as well, and it more specifically addresses exactly how our process happens. Here we have a central processing unit now instead of just a process. Notice that storage is just referred to as a memory unit, but the relationship is the same. And we have within our central processing unit, or CPU, a control unit and an arithmetic logic. Now, the arithmetic and logic unit is the actual circuitry that, say, carries out the addition, maybe does the addition, or checks, say, like a Boolean logical value. So you might ask if a value is true or false, or compare a value. That would be done by the logic. The control unit is what gets the line of code, say the request to do the addition, and then make sure that the chip is set up in such a way that it performs the correct arithmetic, say addition versus subtraction, on whatever data it is given. So the data still comes in here from the input. The control unit looks at the code that it's supposed to run and makes sure that that data gets acted on correctly by the arithmetic unit, and then we still produce some output. Now, of course, we have storage here in order to get values from memory and store values back. Modern computers do work largely on this von Neumann architecture, but there's an important kind of variation to talk about. So a von Neumann architecture computer only talks to memory through essentially one path, meaning that both instructions and data can only be retrieved from memory in a single kind of step. If I'm getting an instruction on step 1, I have to wait to get any data that might be related to that instruction until I get to step 2. I can't go to memory and retrieve instructions and data at the same time. A Harvard architecture computer is essentially a von Neumann architecture computer, and we see this over here, that has paths and ways to talk to separate memory for instructions and data. So in a Harvard architecture machine, instructions and data do not occupy the same exact memory. They actually occupy different memory with different paths to get to that control unit. Modern computers are often thought as being von Neumann architecture. And this is largely true, but it depends on how you look at memory. So we're going to talk a lot more about this in the future, but essentially a modern computer is actually something that's known as a modified Harvard architecture, because there is some separation, but it's only in a cache memory. Now, because of the way that memory is devised, where you have your RAM or your main storage area, and then you have different levels of cache, and those levels of cache are in between the RAM and the central processing unit. Because that last level of cache is separated into instruction and data parts, that is why we consider a modern computer, at least one with cache, that's separated, a modified Harvard architecture. Now, most computers like desktops, laptops, do fit that definition. So it's a small distinction, but an important one. So that concludes our talk on systems. This is a really powerful high-level concept that is very broadly applicable, and it is a little bit deceptive in how useful it is. It doesn't seem all that useful when you're thinking like, I want to write code, or I want to write the next game, or whatever it is. But when you're actually thinking about things at a new level, where you want to devise a new solution, a better solution to existing problems, understanding systems as a whole and those interfaces and how your solution can actually work with existing interfaces and make a difference is a really, really, really powerful concept.